So welcome to the session. So this is the second part of the acid bases pKa weak acids, weak bases session. So we will continue with the last thing we ended up with last time. So we finished the quick revision here, and then we spoke about Ka and pKa and how to choose the strong acid. The next thing here, we have a question. Well, obviously it's not presented in form of question, but anyway. So HF, hydrogen fluoride, is a weak acid, and the Ka is given to you, and you are requested to find the pKa. So pKa basically you get from this formula. So pKa equals to minus log Ka. And Ka here is 7.24 times 10 to the power of minus 4. And then you will get the value of this number. Okay, so let's just work it out. Here 4 and minus raised to the power 10 times 7.24 equals 2, and then the log, and then minus the log is 3.14. So the answer here is 3.14. Okay. The next question, you are given a solution of formic acid, and the concentration of the solution is 0.025, and the pH of the solution is 2.75. Calculate the percentage of ionization and calculate Ka of the formic acid. So since they are talking about Ka of formic acid, that means formic acid is a weak acid. So let's write down the information we have. So we have a starting concentration of 0.025 molar of the formic acid. And pH is 2.75. Okay, now since it is a weak acid, so automatically you should write the equation here. So COOH, it will ionize to give the HCOO minus and H plus. And normally in this type of questions, you need to do the ICE table. Okay, so initially, we have initial concentration, and then you have the change, and you have at equilibrium. So how do you do this? Now, to start with, the initial concentration is the concentration that you are given in the question. So all you need to do is basically put the concentration here. Now, if you are given number of moles and volume of the solution, then divide the number of moles by the volume to get the concentration. So the concentration is given to you. Now, obviously, because this is a weak acid, so not all this concentration will convert into HCOO minus and H plus. So initially, we had this concentration, and we had none of that. So it is 0 here and 0 here. The second step in the ICE table is just basically to plug this value, minus X plus X, and here plus X. So what is X? X basically is the amount that will dissociate from this one, which will increase in the solution of the number of moles of the negative ion and the positive ion. The final step is to add these two steps together. So just 0.025 minus X equals to 0 plus X, which is X, or plus X, and here plus X. So the key thing here is, well, we'll see if we can find X somehow. So as you can see, X here is related to the negative ion, and also it's related to the positive ion. Yeah. Recording? Yeah. No problem. So here we have the positive ion, which is hydrogen, and negative ion, which is HCOO minus. So the key thing here is that we need to find out the X. Here we were given the pH. pH is 2.75. So as we know, pH equals to minus log concentration of hydrogen. So, and we are given the value of this, which is 2.75. So if we want to find the concentration of hydrogen, we need to do the anti-operation of this, which means that this will be 10 to the power of minus 2.75 equals 2. So here we have 2.75 So this will be our X. X equals to 0.00178. Okay, now since we basically have the X, we can apply, and the X is here, and find out the ionization and find out the Ka. So let's find, to start with, let's find out the amount that has been decreased, and amount has been increased here is known to us. So X, as we said, is this value. So we want to find out this amount minus X, that we will use it in Ka. So that will be 0.025. Let's do it in here. That's minus 0.025. Of course, it has to be in positive, so this value is 0.0, just to get the exact number, 23. Okay, so Ka in this case equals to concentration of these divided by the concentration of the initial concentration. So here we've got the concentration of this and that, which is basically 0.00. Since I took 3 digits here, I will do the same thing. Maybe I'll add a digit just to make it more exact. Yeah. So 11178 raised to the power 2. The reason is because you have X and X as X and X both equal to this number. And since here we basically, okay, now normally when we solve these problems, we say that this amount here, 0.025 minus X, approximately equals to 0.025. Fine. And we solve the problem to reduce any sort of mathematical complication. But since we know the value here, so we shouldn't ignore it. So we should just basically use this and plug it in here. So this is basically 0.0232. And therefore, basically, the Ka will be the division of these two values. So let's do that together. So that's 0.00178 times that's 1.36 times 1.36 times 10 to the power of -4. And the x here is basically the amount dissociated, which is this divided by the initial volume. So the percentage of dissociation is this x here, which is the, in case of H plus. So this is 0.00178 divided by the initial concentration, which is 0.025 times 100. So the overall is so the percentage of ionization is 7.12%. So it's very sort of little percentage of ionization as compared to the strong acids where they ionize in 100%. Okay, so the next question here, we have nitrous acid, HNO2, has a Ka value of, as shown, and calculate the initial concentration if the solution has a pH of so and so. Okay, again, we have a weak acid. We are given Ka. So the first thing you should be thinking about after you collect all the information is establishing the ICE table. Let's put down the information we have. We have Ka, I'll not write it, just will underline it. And also we have the pH here. pH basically, it helps us to find the concentration of hydrogen. So if we write the equation HNO3 and O2, it will dissociate to give us H plus and NO2 minus. Okay, now if we want to Ka equals for this dissociation, H plus NO2 minus divided by the initial concentration, which is NO2, HNO2. Okay, so now basically we need to establish the ICE table. We have, as I said, we have this reaction. I'll just write it again so it is tidy. Okay, so initially, basically, we had an initial concentration that we need, and we are given the pH, so we can find the hydrogen ion. So in this case, you need the initial concentration, and that was 0 and 0. And then this initial, then this one is minus X plus X and plus X. And here is the initial concentration minus X. And here 0 plus X is plus X. And 0 plus X is plus X. Fine. So, so basically, we have Ka. So Ka can be plugged into this equation. So if we just write this in here, so that's a 6.4 times 10 to the power of minus 4 equals to, okay, now we have X and X. We are given the BH. So the BH basically, BH, it can be converted into X's, and that will be, what they call it? That will be the minus value raised to the power 10, 3.65. So equals to 3.65 and negative power 10. So that is 2.24 times 10 to the power of minus 4. Okay, so here basically you have 2.24 times 10 to the power of minus 4, and this is raised to the power 2. And then you've got the concentration when you want to apply in this, because you are using Ka. And okay, just a side note here, whenever you want to use this equation, all these concentration, they have to be at equilibrium. So you can't use this row, you can't use this row, you must use this row. Is that okay? So if you are, let's say an example, if you are told that everything was at equilibrium, then you can use these straight away, these values, you can use them straight away. So now here, basically at the bottom, we will put the concentration, initial concentration, minus X, because it is that concentration, and there is a value of X has been removed from it. So here we have the concentration, let's say C, minus X, which is 2, because since we know X, we shouldn't ignore it. 24 times 10 to the power of minus 4. So basically, all we need to do is to do a cross multiplication and to find the value of X, the value of C in this case. Okay, so the next question here, we will solve it. We have another 2 questions, and these 2 questions we'll solve them in the next session. I hope you enjoyed that, and I'll see you in the next session.